So,
Uh, let's get started. Today we will finish this set of slides. Uh, then we will approach data. Okay. But so just to one thing to remind you that the class for next Wednesday will be rescheduled to class at the end of semester because we will book the B.A lab to teach you how to do R, which will be optional. But we will I will put the announcement as well. But there will be no class on next Wednesday. That will be relocated. So the goal today is, of course, to end this topic. So we will be walk through again the continuous distribution, especially the normal one. Go through it again, and then we would be working on giving you more ideas on the related one. Okay. So just to quickly review random variable, just repeat is to just give number to outcomes of the random experiment, which essentially usually is your measurement, right? You are measuring the outcome of your future by a number, whether it's by a integer, then it will be a discrete random variable. If we use decimum number, and the way we do is called the continuous random variable. And the idea why you have to distinguish the two is because of the application or the way that the math tools that actually require for continuous require some calculus. So that's why we are a little bit less rigorous for that idea, but the idea is same. And for discrete random variable, what we do is the big P, and for the continuous one, for all the calculation, we will use the big F. Okay. Just quickly remind you, and then we will do the continuous again because that will be something that we'll be working on most of the time. So just to remind you, for continuous random variable, the idea is that the continuous version has many numbers. So it is not feasible to say a particular number would have positive probability. A range of number can be, but a particular number will have probability 0. So to have a px would be a not well defined. For big F, x will be defined because you're talking about a group of outcomes that actually have positive probability. So that's the reason why we focus on big F. And the motivation, if you recall, would be because of the big P and the big F is by, remember, stacking the big P, you got big F, right? But as you have more and more outcomes, the height of the P will become essentially 0. So P is no longer meaningful. Okay, but F still is a meaningful concept to look at. And instead, before we do that, the continuous random variable here is we have the big F, and for application wise, these two formula will be most of the time we need to do the calculation. Okay. So for the small f, the definition could be what we call density. Essentially means that the probability within A and B, right, will be the distance between A and B times f. Okay. So just to draw a diagram that would try to illustrate the idea will be if I have an f, right, f of x, right, I have an x here, I go from A to B, right, and there's some f, right, and what it means that the probability that x is within this range, right, will be, right, will be this distance, right, which we call this distance, right, is b minus a, right, and the height, okay, is called f of x for some x between a and b, right, especially when this a and b is very small. So this would be an appropriate approximation, right? If you learn calculus, that is what integration it means. So that's why this is the area, right? If you try to draw a bar graph, right? So that's why this f, small f, essentially said the following: the area under this small f curve would be the probability. So that is the thing that we'll be using for the rest of our semester. It's because of the way that things being defined. Okay, so that's how you define f, right? Is the area under this f is the probability. Okay, so I'm not going to talk about that, but this would be the graph, right? If you want to look at the area before a is f of a, right? F of a is the probability x less than or equal to a, right? And because of the area under the curve must be 1 in total, right? So if the left hand side is f of a, the right hand side is 1 minus f of a, right? Because the total area under the f is the total probability, and total probability must be 1, right? The left hand side is fa, the right hand side is 1 minus fa, and the area between a to b is fb minus fa, right? It's area on the left of b minus the area left of a. That is the idea behind this f, small f and big F. I hope it's more clear. And just to remind yourself, topic 1, when you're given a complex data, you want to represent it using mean and look at how good is the mean, look at the variance. Same here, right? In order, we have the description of the uncertainty in the future can be summarized for continuous variable by big F, right? If discrete is a big P. This is can be a complicated object, can be a complicated shapes. And if you want to use a number to represent this complicated future, right, we will use expectation and variance. The same idea, right? Just like you imagine hypothetically, you repeat this experiment many times, right? And each outcome you're measured by the continuous random variable, you have many numbers, and average of those is the expectation, right? And how variation is spread out of this number relative to the expectation, we will call the variance. I hope this is clear, although the notation look crazy, but that is what it means. It's no different from the discrete version. If you try to look at why integration is explanation, but I don't want to bother you with math. Okay, so just a very quickly review of uniform, exponential, and normal, because the rest of the 3 we just barely touch it. Then we will talk about Excel. The reason the last 3 we only touch it a little bit because we will be using it later in our semester. I just put there to put all the things you would need for this semester here. Okay, it's just a preview. And indeed we're not even going into detail even in the later stage. So that's why I just put there. But for us, it's just another table to look at. Okay, so that's nothing very special. So you will later notice after this class, basically what you learn is basically some procedural thing. We want to do something, and we'll learn some process to do stuff. Okay, so actually the same for our whole class, right? The first look the mean, right? You just learn mean, variance, various measures and procedure to do things. So you understand the algorithm, the logic, and how to apply them. That's the main goal. Okay, of course, if you want to go further, probably you will want to learn why the two, what's the mechanism, what's the reason behind that belong to statistics. For our class, we are learning statistical analysis, so it's not theory. So just like how to learn the tools, just like your computer, right? You know, press this button, click this icon, that will work. Okay, but we don't know the mechanics, the codes behind why it works. The same idea. Okay, so we just tell you the tools here, then how to use it. Okay, so uniform, the main idea uniform is try to illustrate you how small f and big F is related. But in addition to that, uniform will tell you this is the way you will start if you have no idea what's going on for the future, right? Suppose and remember the example I often said is you switch on the TV, and there's a so-called expert in the financial market predicting the future. He will say, okay, today's the Hang Seng index is going to be 16,000 to 17,000, right? And how does it, I mean, they just tell you the maximum and minimum, right? And they never try to explain what is the distribution of the future, right? It's incomplete. It's just the range, right? So if you believe in him, ever trying to do a prediction, right? And likely you would try to predict using a uniform, right? Or of course you can do normal, but uniform is one way. So either use normal uniform would be the way if you try to model things that you don't know how to model. Okay, because uniform we just try to put every single point in the possible range, right? And equally. So that is the way to do. And you would ask, okay, besides that, what you're going to do is if you're talking about something that repeatedly appears, then the Bayes theorem will help us to starting from a uniform. We try to learn, and that will get more accurate. Okay, and that will be the tools that usually you would start with the uniform. Okay, and I'm not going to the detail because they're not important, right? The only thing probably you need to know is the big F, right? That will be a complete description of the random variable you would like to have. And the mean and variance will be the representative numbers that you want to convey, right? Is that clear? And this is an example trying to tell you how you do those, but I think it's straightforward. I'm not going to repeat. The next one is for exponential, okay? And probably you can remember what is the use of that. Yeah. The first line, right, is waiting time until something happens. Okay, if you try to model this is the tools, and remind yourself what is the assumption behind this is when this is a good model to model time for something to happen is you would consider this a Poisson. Okay, remember it's Poisson. Poisson comes from binomial, right? But what's binomial? Binomial is saying that you open n different boxes, right? Each box is independent, and the box have a successful with probability p and failure minus p, and each box is independent, right? And how it extends to Poisson, right, is you consider each second or each minute is open a box, right? So you count how many number of people would come in, right? Is how much success. And as long as each time period is independent, then exponential is fine. So it means that no matter how long you wait, okay, after if nothing had happened, your viewing of the future is the same. Okay, that's I hope you remind the idea we said of the stone statue of looking when your husband or wife is coming back. right? You often go to a tourist site, is near the sea, and there's a hill or mountain where there's a stone, a humanoid figure. People would have a story saying that there's a man and woman who his partner actually go overseas and waiting him to come back, right? And why become a stone? Because he keep waiting every day. He's thinking tomorrow his or his wife or her husband is going to come back. And no matter how long you have wait, you always think tomorrow he or she is going to come back. It's meaningless, right? It's not saying that the more time you wait, it's more likely. Okay, given that you have wait, it hasn't appeared, then the same. If this holds, that is exponential is fine. And this property is called memoryless. There's no memory. Okay, it's like the goldfish, right? After 3 seconds, it forgets. Okay, so I'm not saying that this is obviously the right thing to do, but this is starting point for learning how to model a process. Of course, this is the starting point, and this is the thing that usually people use. And of course, there are more complicated way to model it, but this is starting point for our introductory class, right? Just like you learn physics, you learn Newton mechanics, Newton first law, second law, and third law, and then you always in the learning you forget the air resistance, right? When we talk about the gravitational thing, why the Earth rotating the sun, right, that's right, rotate the sun. Then you just focus on the sun and the Earth, right? You forget about the Mars, the Jupiter, Venus, all they also in the system, right? But it's okay. I mean, they are minor thing, right? Although we remember the assumption is meaningless, if not, they are affecting your result greatly, it's fine. You just make those assumptions, right? You just ignore those minor points. So that is the thing. And then you would remember the big F here, okay? The big F here is this one. And this turned out to be the exponential idea, right? Why I call exponential is, remember, the curve of the F look like this. Okay, the F look like this. Right? And you would be looking at the mean and the variance, right? We'll be looking at 1 over lambda and 1 lambda square. So this is have to be careful. The variance is no longer the same as the mean. This is different from Poisson. Okay, and those of you who try to have this slide, I put it here because I try to see is those of you try to read our textbook, or maybe look at Wikipedia. They may look at they use different way. They use beta, which 1 over lambda, and then everything becomes similar, just the way they define things. Then in that case, mean will be the beta, which the time they come. So, but the same thing. Depending on the book, they'll be different. But the reason why I use lambda is because of it's close correlation Poisson. So I don't want you to have a remember one more variable. So that is, I think that's more direct. So now let us go to normal, and I will be further slowed down because that will be the most essential thing you will learn from this class, is bell curve, and we'll use it for the rest of our course. So the bell curve is very important. So I want to make sure that everyone is on the same boat, because if you don't know what's going on here, you will be super confused for the rest. I hope it's clear. If not clear, let me know, because today's goal is not very ambitious. We want to finish this set of slides. Okay, it's not ambitious goal because we finished this. It's about 6 weeks, and we finished half of the material, right? So I mean, it's not, you're already ahead of schedule, so don't worry about that. I mean, so if you have questions, please let me know. I mean, we can slow down, because I have said, right, in my time when I was student 10 years ago, probably exactly 10 years ago, and then I learned this. We spent whole semester up to here. Okay, but now we only use it half semester, so it must be hard for you. It's very hard for me at that time. So I can imagine that can be even harder for you, because you just learned it in 6 weeks. So if so far you don't feel too much pain, then congratulations, actually better than mine. Okay, but of course, you guys should not be very proud of it, because at my time, I don't have internet, so I have hard time. But you guys have internet, you can look at the video and check it back, and then much better. Because still at my time, the teacher is still writing on the whiteboard, and then it's very far away, right? It's a big lecture theater, so it's very hard to see. Now you have everything on your iPad or the computer, then you have much better condition than we do. Anyway, the bell curve, okay? This normal is the bell curve. And we will learn later, I think, in topic, 2 weeks later, by the end of this month, you understand why normal is so prevalent. And this is what we call the central limit theorem, okay? But we'll be more careful at that time. And one thing you have to look at is the support of the normal, which is what value can do is from negative infinity to infinity. So that essentially means every number is possible, okay? No matter what you look at. And some of you would immediately say, okay, but every number is possible, but how does it fit our idea? The usage case is like the IQ, the weight and height, right? IQ is measured by how many questions you can answer in a test, right? It cannot be negative, right? The worst thing is 0, right? And then how you can put it, right? And I would say, if you are aware, last time we said, right, 99% of data actually within 3SD, right? So as long as the mean and the 3SD, right, mean subtract from 3SD is far away from 0, you don't have a problem, right? If you notice, right, the IQ, right, I think the mean depends on which location, but in the global sense, it's like 100, right? That is what defines IQ, right? And the standard deviation, SD, is like 15. Of course, depend on where you are, but of course, I think Hong Kong has one of the highest IQ in the world. It's like among the top 10. It's like the average is like 115. But anyway, we have 1 SD above. I mean, our average in Hong Kong is 1 SD above the rest of the world. But anyway, you can imagine 3 SD is minus 45, right? 100 minus 45, 55. So it's very difficult to below 55, right? 99% is like 55 and 145, right? If you happen your IQ is more than 145, then you're extremely smart already, right? 1% in the human distribution. So that's why it's okay, right? There's no way you can go to 0. I mean, for essentially the modeling purpose, right? Although the model will say, okay, you can go to negative infinity, but it's not a concern, right? For any decision, there's not a big issue. Okay, same as IQ and height. So weight and height, right? There's never negative height, but it will fit very well. Okay. And one other thing is, you look at binomial, Poisson, exponential, probably not exponential, but binomial or Poisson or hypergeometric. Look at the graph. It is essentially a bell shape. Just go back. Sorry, a little bit go back, but I hope that would be a little bit clear. Look at the binomial. This is Poisson. I go to binomial first. So look at the binomial. Look at the pink one. Okay, you see this one looks very similar to the bell. Indeed, that is the case. We'll state the theorem in the maybe 2 weeks later. We will say, actually, when n is big enough, okay, the binomial and the normal will be so similar. We will use this to do a lot of calculation, okay, and to simplify our life. But when binomial is, just to remind yourself, later you will remember as well, is when n is big enough, binomial and the normal will be very similar. Okay, so that's why you can imagine binomial is a very common thing, right? You ask people yes or no whether they like I don't know, they like spicy food or not, right? Then you look at asking the data, right? Then that actually turned out to be binomial, but if n is big enough, then it's a normal. So that's why normal is so important, because of many of things we learn actually turn out to be normal. And if you look at the Poisson, right? the Poisson, although start from 0, right, it's a little bit skewed, right? But if your lambda is big enough, okay, so if you put the lambda, then you're actually pushing this, right? And if you pick a very big lambda, and that turned out to be very similar to normal as well. So everything is like quite normal. And similar to hypergeometric, look at the graph here. Okay. Although we don't do any proof, but you can see it's like bell-shaped style. If n is very big, the big N is super big enough, then everything becomes normal. So that's why I hope I explain why normal is itself actually, when we talk about a very big sample, very big cases, the binomial, Poisson, or exponential, sorry, hypergeometric, right? All of them looks like a bell shape. So that's why bell shape is so convenient, okay? And that's why you need to learn that, because it's a good approximation. And why is it useful? Because remember the empirical rule, right? Because if you don't want to do any calculation for rule of thumb, you will see that things is 70% is within 1 SD, right? 95% 2 SD, and then 99% within 3 SD, right? The rule of thumb. And that tells us how you make decision, right? If you don't have computer next to you, okay? Now let's go back to the normal. And so normal actually look at this particular very crazy expression of square root pi and e. But do know that the main thing you learn from here is to notice this thing is has the mu and sigma square, which essentially from topic 1 you would guess is the mean and variance. And turn out that only the mean and variance matter, right? And mean is controlling where is the peak, right? Variance is looking at how flat are the tails. Would be how spread of the distribution, right? Because of this is symmetric among 0, and the kurtosis is always 3. Okay, so so that's the idea. So add one slide, because I think in the other section, some people are not happy with my hand waving argument. Normal is very normal, is very common. So what are the application? Okay, although you will learn the application for the rest of this course, I give you application outside this class in order to convince you why this is the case. And probably some of you study finance would notice asset pricing. A lot of time they assume normal. Okay, stock price is moving normal. That's how they work on it. Interest rate or asset price. And one of the most famous model, probably you might have heard that, is pricing option. Okay, and the famous model, the formula is called Back-Scholes model, and the Back-Scholes model indeed assume normal distribution. Okay, and that is one of the equation that earn Nobel Prize, right? And if you learn option pricing, that would be a 4,000 class in finance. But anyway, that is what it is. And if you do risk management, maybe accounting people would care, or finance people would care, is how you would evaluate the probability that something would happen, right? How likely your portfolio is going to loss, and you look at the value at risk, right? Or expected shortfall, or they also need a normal. Okay. And the last one I want to put at is quality control. And the reason will be clear is when you do production, and production has a lot of randomness, because you deal with the nature, and it's a combination of many different random process. And that's why, as I said, the central limit theorem would say many random process would have a normal. So that's, I put it here. I hopefully would convince you why normals is important, because there's so many applications. I just list some of them here, but nevertheless, you can, now the internet is so convenient, you can just check it out if you want more. But I hope I convinced you that normal is so important, not only for this class, but way beyond this class. Okay. So just quickly review again the notation. The big X, if I say the random variable X, for normal will be a snakes with n mu sigma squared. And here is the property that I want to emphasize again, because probably some of you still ask me is why do we care about this property? Okay, because of if you remember the formula, if you multiply some constant plus some constant, right? And actually this is same for the mu and the variance, right? This is the formula that you learn. Even this is true for everything, right? It's nothing special for normal. What is special thing is, even if you multiply your normal random variable by a constant plus a constant, is still normal. The reason why this is important is because you can always no need to look at every single normal, but you can always transform to what we call standardized normal, the normal with mean 0 and variance 1. By doing so, you will simplify all the calculation. This is exactly what all we do for the rest of the basis for the operation that we do for the rest of the semester. It's called normalization, and probably you would learn some of time. If you learn in the high school, you learn set score, right? And that they tell you is minus the mean over the SD, and they would do it all the time. But I would tell you that this is not a valid. This is only valid if you have normal. It's not valid if not normal. The reason is you do this, it's still a normal, so that's why you can compare, right? Because of why you can compare, because you can why you look at C score. Aside, look at, you try to compare people performance, say in this stat class or compared to accounting class, right? You can look at how well people are performing in two different classes. Then two different classes have different mean or different variance, and how can you compare? Then they tell you to compute Z score, right? The class that you have higher Z score means you perform better, right? That's what they teach you when you do in the high school. But this would assume implicitly the two class, the score actually a normal. You follow normal, this is valid, right? If actually one class follow normal, the other class follow uniform or other distribution, it not be uniform or whatever normal, then this comparison is invalid. Okay, so you have to make sure that when you do this kind of Z score or what we call standardized score, I mean, have to be the right thing. Okay, and probably that's the reason why you learn our CHK has a unique process of grading, right? We have say we do not have a fixed curve anymore, right? So it depends on how well you achieve our learning objective, and the teacher have discretion of giving who got A or get A minus or get B, because of we no longer believe that, I mean, every single class should follow a certain distribution, right? In that case, that's the reason. I hope it's clear why this case. But even though if you don't get that, then you should follow our procedure. How do we get those? So that is that table. And there were two versions. And for most purpose, you can just use one of them. But we can use both. Okay. So look at this example again. I hope I can convince you this is a very easy operation. So I want to look at the Z table is, I want to calculate probability Z less than 1.4, okay? And probably it's not entirely clear why we want to do that, but suppose we want to do that, I mean, just some operation first, okay? Z means the following, right? Z means it's a mean 0, sigma 1 normal, okay? So this is the the bell curve we have, and what we have is asking 1.4 is here because it's on the right of 0. Okay, it's asking this probability, right? Because this is the F curve, right? So I want to look at the area on the left-hand side of 1.4. And I already tell you for normal, there's no way to calculate this area directly. The only thing is either use Excel or look at the table. Okay? And how to look at this table? Later today we talk about Excel, but look at the table is to check what's the entry of 1.4, right? Because we have this F table directly, right? This is the F of 1.4. Okay, and look at the table, and I put it on the slide this time. Okay, this is for negative value, and we can look at the positive value. This is the same table. You go to the internet, look at the Z table, the same. I just put it here because it becomes easier for you to reference. Okay, so look at 1.4. How you read this kind of table? Typically, you would try to look at the first column, look at the number you look at, and look at the second column for the second decimal places. So 1.4 is looking at the column of 1.4, right, which is here. Okay, and because 1.40, that means that it's the second column, right? If 1.41, look at this, the other column. Okay, for those who don't have this on the slide, because I just put it there instead of separate another one. So, but this is table. You can look at the Google or Bing or whatever search engine, just everywhere. Okay, so it's just this number. Okay. Of course, later when you look at the Excel, you will see this is even more simple. Okay, I hope that is clear what's going on here. Okay, and the next item we want to check out is Z less than negative 1.6. Okay, and this one I'll tell you we can do it in two different ways, right? So draw this again. Sorry, there's a set. Okay, 0 is the middle, the bell here. Okay, negative 1.6 is on the left hand side of 0 because it's less than 0, right? And the area they want is this guy. Okay, so there are two ways to handle this. You can look at directly the negative table, which is essentially F of negative 1.6. All right. If you have this in your entry, that is immediate, right? Because that is what it's supposed to do, right? Look at the area on the left-hand side. And the other way around to think about this is this area, because this is a symmetric curve, you can look at 1.6 here. Okay, and the green area should be same as the purple area, although I didn't draw symmetric, but you see the idea, right? The green area should be same as the purple area. And although the table we have don't give you the purple area, we can find the area on the left-hand side, right? Which is the red area I want to draw, right? The table we have, you can find the red area, right? The red area, right? Because the red area is F 1.6. Okay, and that means that the purple is 1 minus F 1.6. Okay, so because the total must be 1, right? So that's the idea. So let me do both ways to make sure that you understand what's going on. I look at F negative 1.6 for the first trial. The second trial, look at the red area from the positive F table, the Z table, and then subtract from 1. They will give me the same answer. Okay, so let me do it. Okay, let me look at the negative table here. Okay, negative table, negative 1.6. Again, look at the first column. Take up what is negative 1.6 here, which is this guy. Okay, and it's 1.60. This is what we want. Exactly this guy. Okay. And the other rerun, as I said, you look at f of 1.6 and subtract from 1. Right? This is the first way. And the second way will be this one. Look at 1.6 and this number, and you subtract from 1, right? Of course, you would say this is too old-fashioned look at table. Why don't you use Excel, okay, or calculator? The reason is you're not allowed to have computer in the exam, so we have to use it, right? I mean, this is just directly use Excel. You will learn today. It's a normal this, and that's it. Okay, but you still need to learn how to use table because of we can't allow computer in the exam. Okay, I know it's old-fashioned, but sorry about that. So we have, as I said, the empirical rule, which essentially said the following. Okay, Z, okay, Z is more is looking at X minus mu over ST, right? So Z of -1 and 1 means your value is within 1 ST, right? Because this is the mean, right? This distance actually means 1 ST, right? This is distance below 1 ST, right? Right? So he's saying that within 1 standard deviation from the mean, you have almost like 7%. Within 2 standard deviation, right? It's 95, right? And 3 is 99, right? So just if you try to understand this, right, is you can draw the graph again. Essentially mean the following. If this is X, right, go back to the X. This is the mu, right? What is simply said is you can have mu plus sigma, mu minus sigma. And what does that say is this area is 68%. Okay, 70% of your data should fall within 1 standard deviation. Okay, same for the 2 standard deviation or 3 standard deviation. Is that clear? Okay. So I hope this is. Oh, sorry, I should delete that. So I think last time we almost end here. So this normal, okay, look at X less than 16. So let's do this again. Okay. So the question, because it's too important not to be repeated. So X is here. We have mu is 20, right? And the bell here. Okay. And we know sigma square is 16, which imply sigma is 4. Okay. So what the question is asking, 16 here, actually is 1 ST below. What's the area below it? Okay, so that's the question. Okay. So that's the thing. Okay. And probably some of you may ask why we care about this. It's because later we will see normal will apply to many contexts, and especially sample mean. And then later you will see if we figure out the data is actually 16, then do we want to say something? Okay, do we make some decision? But that will be something we talk about next week. But let's see. Now, how do you calculate this? Of course, you can use Excel to give you direct calculation, but we told you how you do classical way to do it is mu from 20, you just convert it to 0. Okay, the way you convert, remember, is X minus mu over sigma, right? So 20, every number here, 20 will be minus 20, right? Over 4, that will be 0. 16, okay, what's the number? 16 minus 20 is negative 4. Negative 4 over 4 is 1, right? Negative 1, right? So here is the same. Right, just to remind yourself, 16 is actually 1 SD from 20, right? From the mu, right? So that's why exactly is negative 1, right? Because here is Z is asking every number is converted to the distance measured in terms of SD, right? 16 is 1 SD below the mu. So it's actually just negative 1, right? And the red area will be same as this red area. So why this is true? Because that is the property of normal. Okay, it doesn't hold for anything else. This is only for normals. That's why you can do this procedure. And for do this, we just look at the table, right? Because this is just left-hand side. This is just f of negative 1, right? So go to the table, look at what is f of negative 1, then we're done. Okay, go back to here, look at the table. Okay, f of negative 1. Let's go slowly on this one. Look at the z, many numbers. Negative 1 is here. So this is the answer. Okay. Of course, you can do f of 1 and subtract, right? If you don't have next table, you just have the positive 1. How can you do it? Because symmetry. Look at this number f of 1. Subtract from this guy, the same, because they're symmetric, right? So I'm not going to further review that one. The rest I think should be clear. So I want to take a little bit more time because for break, because I think that would be good to end the normal. Here is two property that are not immediately clear why they're useful, but will be clear very soon in the coming semester, coming weeks. Is we have a very nice property of normal is you multiply by constant plus a constant to normal. And actually normal is even more amazing is if you have two normal x and y and they have different mean, different variance, and if they're independent, that's important. If they're independent, okay, that means that some of them remain to be normal, and that's essentially why a lot of things we observe is normal, right? Because of your your weights, right? Depend or IQ or height. It depends on many natural factors, right? And many natural factor is again determined by many natural factors, right? You can imagine how your IQ comes from or the weight or height depend on your DNA, your dad or your mom, right? And again what you eat and how you grow up, all the things. Okay, many factors come together. But remember, your dad and mom also depend on their dad and their mom, their grandparents, and a bunch of factors, and so on and so forth. There's a bunch of factors, right? So if everything is normal, Arab is normal. So that's why everything is normal. So that is the reason why you see normal all the time, is because of the bell actually turn out to have a many amazing property, and turn out not only addition, subtraction the same. So that's the reason, right? Because sometimes factors are conducive to your height, and factors are not conducive to your height, right? Adding, subtracting, the same thing. Okay, so that is the one of the reason why this is important. But we're not going to detail why they are right. Instead, graphically, we will see this, okay? And you will see later, you will see why this is useful. But this is a graph. If you have normal is x and y look like this, the blue and the red, add up together become the blue one, okay? And this is still a bell. And you have this light blue and light red, you subtract them, it's still a normal. So this property is very important. We don't prove it. It's not hard to prove it. But you notice even though you subtract, the key point is variance to adding. Okay, that's the mean subtracting. The variance is not reducing, okay, because they're independent. Okay, so maybe I just spend 1 minute because I can define it very quickly. This one, there's nothing new here, beyond definition. There's nothing to understand but definition. Even though you go to a stat department, I don't think they go beyond this very much. Okay, because to understand this fully is very difficult. At least at the introduction level. But what it is very simple. Okay, if I have a bell curve, okay, the idea is very simple. I draw a graph, then it will be very simple. Then you understand immediately what is a chi-square. Okay, so now I have a bell, right, which is very common, right? But instead, I don't look at this number. I just pick a number here, right? And I square it. Okay, I have a normal here, and I square it. Okay, and right, this can be negative infinity to positive infinity, right? That is what it said. But when you square, what do you have? It will be start from 0, right? Because the worst case is 0, right? Square must be positive, right? So the f would look like what? Maybe I erase this. Right? F look like something like this. Depend on where you are, but maybe I should be more careful. I should look at the z. Okay, I look at the 0 here. Okay, and I look at the z, sigma 1, sigma square 1. Okay, and I square that guy. Okay, okay. Look at each number, I square it, and this is what this looks like. And probably ask why we would care this guy. We will care this guy when we go to later stage. Okay, and later this is actually modeling variance, because y squared, because variance is taking subtracting mean and take square. But it will be clear later why this related to variance idea. But this is we will be talking about the variance will behave like chi-square. And probably you ask why the chi, not x square. It's because in old day, when people print things, they pick up the stamp and right, and then the worker, they can't distinguish x and chi. So that's historical error. Everyone now call this chi supposed to be x squared. Okay, and that is what we call the first statement, z squared. Standardized normal and square is the chi. So this is the first thing you need to know. Okay, and second thing you need to know is if you adding up many chi, okay, that will be what we call chi-square n. Okay, that's what. That's the only thing, the two facts you need to remember. Okay, or you just know, not to remember. No one actually asked you this guy. I mean, I will never ask you this, but you just need to know what's chi-square. Just simply this. Chi-square is simply the normal, standardized normal square. And chi-square degree of freedom n is just n of such thing add together. Okay, if you want to remember this as you want to remember, but otherwise you can forget about it because there's no one will actually ask you what is chi-square anyway. Okay, unless you go to interview for a job for statistics. Okay, no one actually asks you for that. Okay, and probably it's good to see how it looks like with bricks after this. Okay, the chi-square of 1 look like this guy, because a lot of things is 0, right? Because you say center is 0 and you square, and most of them actually is nearby 0. Okay, and when you add more, it look like this guy, and you add more and more, actually look like a bell, and turn out to be probably not surprise to you if the chi-square of very big n actually a bell curve again, which is surprising, right? Because you can imagine that you square, add up many of them, actually still a normal. But anyway, it's not our concern. The chi-square later you learn will define t up to the break and after the break. Okay, so later you will see we only give you some definition. We don't even bother to give you application. Here I just introduce them because you will need them later. I just talk about them. So there's nothing to remember at this stage for the t and the chi-square or the F. We'll talk about this later. But before that, let's have a break of 15 minutes. In the meantime, I'll put the U reply. So I'm sorry we overrun a little bit for the break. Let's resume at 10:42. Okay. Don't worry, we have enough time to go over the Excel and other things as well, because we cover all the theory already. There's something we didn't talk, but they are not super important, just to review. Later we'll talk about that. So let's have a break. In the meantime, you can fill in, and I go around to see if any question that you might have. Thank you.
So let's resume. Let's see. Okay. So hopefully it's not that bad. Happy Friday. Yeah. Do you mind explain again why can't we? Oh, the reason is very simple because when you have continuous random variable, it means that you have many values, right? Probability mass function means you have to put probability on each number. Okay. The probability each number is essentially 0. So you can't, right? You remember, I think these days some of YouTuber try to explain the case of I think American Wonderland, right? I think you remember there's a rainbow thing, right? The red, green, I don't know, and blue, right? And there's a game, it's a guy who tried to throw a coin to this one, right? And they said the coin is bigger than the width of the rainbow, right? 美國夢險樂園, so that's a reason. And then, and when someone explain, you're never able to win because this is only the point in the probability that you hit on that is essentially 0, right? Because of this only one point. I mean, there's no way you can hit it, right? It's very hard to hit the particular point because otherwise you just slightly off, then you can't, right? So the idea is same, right? You can imagine you try to particularly try to fold your stuff here, right? And here particularly, that is almost like 0. So that's why you can't use it. Okay, just for example, in this way. I don't know. I mean, everyone has hair in this room. This no offensive. So you try to pick a particular hair. Okay, if you try to pick a hair, okay, and try to dye it a little bit. Okay, maybe dye it like a golden color. Okay, and I ask some of you to pick a hair out of me, then probably pick up that hair would be 0 because there's so many hair. Of course, you pick many times and you will eventually pick it out, but you just pick once, then you will be unlikely to pick the same one. The same idea, right? Because hair is still finite, but you can imagine that you have many hair in this room, okay? And I dye one of his hair. I randomly pick up one hair, then it's unlikely to pick up his particular that one hair. You see the logic, right? Or you in the sea, right? On the Pacific Ocean, right? That particular fish, maybe Nemo, right? Whatever fish is there, you particularly get that fish is eventually 0. Essentially 0. The same idea. I hope I answer your question. But that is philosophical idea, but just like the reason. If hopefully I answer that. If not, then you can ask me again. Difference between X and Z. X is the standard normal. It's a normal, can have any mean, any variance. Z is particular, have mean of 0 and variance 1. Okay, and how do they relate it? Because we don't want to have a F table for every X, right? Because that will be a lot of table. So that's why we always look at the table for Z and transfer back because they're same. Okay, that is the reason why if X and Z. I hope that's the reason. I mean, we don't care about Z by itself, but we know how to do Z, then they can transfer knowledge to any normal. So that's the idea. Hopefully, why so difficult? I agree. I said it's difficult is because of you don't familiar with that. The reason is being that we don't explain everything in detail. So it's like new knowledge bombard to your head, and your mind actually explode because of the number of the thing you can handle is very limited. Okay, I recently read a Twitter feed explaining something. It's like our human brain is like supercomputer. They can do a lot of calculation, but our mind is actually can process one thing at a time. Very surprising. It's a big paradox, right? Our mind is very so powerful, but when we have more than one thing, then our mind explodes. I mean, probably you notice a business case is that our mind can only at most handle 7 things at most. I mean, you go to supermarket, if you try to buy 7 or less stuff, you can remember. If you try to buy more than 7 stuff, if you don't write that down, you can't remember that. So I mean, our mind is a good processing, but our RAM and storage is a little bit not very good, right? In terms of computer, have a good fast computer, but our RAM and memory is not really good. So I do agree that it's not that easy. Yeah, the weather is perfect for sleeping. Seriously? I thought it was more sleepy when it's sunny. But now today it's very sunny. That's fine. I agree. Friday is always oh, good. Today we have a full understanding today. Okay, little bit windy, cloudy. Yeah, it's fine. So so it's good that I take away people who think it's one. So I think people would accept this little bit more appropriate. Okay. And someone still is not easy to follow, so I try to work on the Excel. Hopefully you will see how we do things again. Okay, I hope there's a good joke here. The chef tests me and asks, how do you make an egg roll? So I don't know. I say you push it. Okay. Proof is good. I don't know. We don't do any proof. Okay. That's a fun one. I like this one. So what does that mean is for those who don't read Chinese, he said, he said, I wait for a long time today. No one said happy birthday to me, and then wait and wait. At the end of that, I know today's not my birthday. So that is what it's supposed to mean. I like this. This is a good joke. Today weather is sunny. Ha 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 ha. Okay, good. Start to getting cold. Yeah, it's no. Okay, good. I hope it's okay. So we quickly define the rest, and that we'll go to Excel. So because this is not something that we will use today, so I just very quickly call the student T distribution. So it's called T. Okay, and you probably ask why it's called T. Later in the next class, we'll talk about this student T, this T, and the T actually related to the name student, like the name student. It's because a very famous mathematician, he proved this, and his pen name is student. Okay. The reason why I have to use the pen name student because I think, remember he is a worker for a company in the US, and he's not allowed to use his name when he do research. So he published his thing using the name called student. Just say sarcastic. But anyway, what is it is the following. So if it's a fraction, the numerator is the standard normal, and denominator is chi-square m. Okay, so basically it's the following. It's a normal, basically it's a z over z square, z square, z square, z square, z square, z square. So I guess the reason why that's why you're so sleepy, because there are so many z. Okay, and we have a z over a bunch of z squares. Okay, and basically normal over normal square, and take a square root. And of course, I forgot to divide how many you have, right? Okay, and this guy turned out to be what we call the T distribution. And in fact, you understand this T is what? T is just a bell curve, but with a fatter tail. Okay, it's a bell, a fatter tail. Okay, and if you get a bigger m, then it will become a normal. So it will be immediately clear for the rest of the class. This T student T bell and then standard bell will be the thing that we use mostly in all statistics. Perhaps surprisingly, if you ask any statistician, T probably the thing that you will use all the time. So if I do data analysis, T is I always use it. Basically, everything I do is T. Okay, I look at this variable, I calculate this, and I do analysis. Okay, this is the thing that I do. I think 99% of the time I do this one. Okay, so this is the thing that you will be needing. Okay, and it looks like a very like the bell curve, but just you can imagine just a bell curve. Okay, but a little bit bell curve, but a with fatter tail. Okay, that's the only thing you need to remember. Okay, and that's the thing you remember. We'll tell you how to apply this, but this is the thing you need to know. That's a bell but with fatter tail. And the last one we'll use it later with an over. It's called F. Okay, and it's not clear what it is, but basically the fraction again, and the numerator is if average of this mz is z up to m. Okay, m of this z, and n of this z. That's a ratio, and this is f. Probably ask why I'm doing that. Okay, later you will see I compare variance, which one have higher variance, that I use the f. That's why you do ANOVA. ANOVA is comparing variance. Later you will know. But ANOVA is the thing that if you go to quantitative social science or go to medical school, they use all the time. Of course, if you do finance, you do regression, but you learn how regression, same thing as ANOVA, more or less. So, but anyway, this we will need for the second to last topic, or the second last topic, we'll do ANOVA, that will go to F. So don't worry about it for the moment. We'll talk about this in the last 3 topics. They call there's bunch of z is basically we'll do comparing variance. Okay, it will be clear when we talk about those, but and you will see depend on how many z you use in the numerator and denominator, it will give you different shapes. So that will be something like this. Okay, depend on how many z you have. Okay, that will be but you can imagine that it's more or less a bell curve, but if the bell is like asymmetric bell, it will be a much fatter tail. Okay, and it's a bell-shaped style stuff, but it's no longer symmetric. Okay, because start from 0 to infinity, so the shape is very weird. But you will see the usage later. I just introduce here because I want to introduce all the distribution we use, and that you can easily come back and check it. Okay, and now of course you can go back to the video and check everything. I think I recorded during the COVID time. Okay, so but now Excel, I hope you take out Excel and then we work on it. As I mentioned, right, we will learn Python, I think 2 weeks later, optional tutorial. No, optional. For our class, the Python will be done in the class. Okay, for this section. So you will be doing after the Chongyang Festival, that week we will do Python. The other section we will do at night. Of course, you can attend at night if you want to. The same thing. So Excel. Okay. So here we will tell you the calculation here. Remember, binomial. The P is what? The P is nx px 1 minus pnx. Right? That is P of x. Okay. And as I said, we don't want to do this calculation, right? Excel will tell you the first one. You give me the x, give the n, give the p. Okay. And the last one is important. It said true and false. Okay. It's asking you whether cumulative or not. So if you use the false, that is give you the p. If you give you the true, give you the big F. Okay. Now let us go to Excel and work it out, because that is the only way that you familiarize yourself with that. So let's do it. So don't worry. We go, at least for the first 3 one, we go slowly. Okay. So remember, we do n is 2, n is 5, right? So n is 5, right? X is 2, and p is what?
I forgot. I think this example is the spicy food example. Yeah, 0.3. So it's asking 30% of the customer like spicy food. And here we come 5 guys. Exactly 2 people like spicy food, right? It's just f of p of 2. How do we do that? It just find this, okay, by normal distribution, number of is the x1, okay, p2, okay, and then we will be n is this guy, right? And then the p will be this guy, okay. Is that clear? How we input those, okay? And at the end, because I want the p, I'll just put false. Okay. And this will be the, let me put the formula here. Okay. So this is exactly what it means by the p, right? And the computer is handy when you calculate big F, right? The p probably say, okay, I can use my computer, I can use my calculator, right? But the big F turned out to be complicated to calculate, right? You have to add up 3. So you have to big f of 2 is very simple. F of 2 is again is by this. I have x and then n and then p and then false. So and then true. Okay. So this is the answer. You can compare this result to the slide that I have. So that's how I calculate. Okay. Of course, I write down the expression. Of course, I'm not good. I do the Excel as a cheating way to calculate. Okay. So I hope you see how I do that. Okay. And that's probably what you will be doing your assignment, right? You list the formula and probably use the Excel to cheat. Okay. But that's fine. Since you are very smart, so that's no problem. That's okay to do so. Is that clear how to do it? Is that clear how to do it? Okay. And probably you can check whether your calculation is right. Okay. Now, the next one, you can basically plot the graph. I'm not going to do that. The next is exponential. That again, I guess is not complicated, right? Because exponential is like this, right? P of x is e negative lambda x factorial, right? This is what it said, right? So you only have one thing, it's just lambda, okay? So just exponential, lambda, then you're done, okay? So let's go to the Excel, okay? And see how it works out. So open another one, okay? Make it bigger. Now it's easier. I have lambda, I don't know, 5, I forgot. And x is 2, say, right? And I want to calculate p of 2 and f of 2, say, okay? And p of 2 will be just Poisson distribution. And you put the x, right? Is what it says, right? X is here. And put the mean means the lambda. Okay. And then you put false for the mass function. So, and then you can have the same thing again. Looking at x and lambda and true. Okay. So this is the how to calculate the p and the big F, right? So you can see it's immediate, right? So that's why I said you don't really worry about the calculation or the formula, right? Of course, you need to know what is input, but the calculator do everything for you, right? And you can change a lambda and an x, and you can do all the calculation you need. You can do analysis based on that. So that's why I say Excel is very convenient, right?
Of course, later you learn R or Python, then you figure out that it's even easier. But I mean, Excel, I think is sufficient for our purpose, unless you go to very deep. Okay. Is that okay? Is that okay? Is that clear? Of course, I will try to put the I put that on the web after the class so that you don't need to worry about that. You can either go back and check. Okay. If that's okay, I will do hypergeometric. Okay. Hypergeometric with the same. So you notice I use the same notation as in my text. So that's why when the Excel will be easy. But do note that when you do R, have to be very careful. It's different, or Python. I have to check what should be the input. Everything I follow this, right? Remember what's the P here? I hope you try to remind you what's the P. P of X is the following. A of X n minus A of n minus X, right? N over n. So that is the thing, right? So here we have the input NaN, okay? And remember the example, right? You have 30 objects out of which 4 of them are good. You take 6 and you say probably 2 is okay. So let's do it, okay? So the question would be, right? You have good, how many items you have is 30. How many of them is good? I think it's 4. And you want try to pick up 6 items from the warehouse, and you want to look at the probability 2 of them is actually a defective. Okay, the question, remember, total item in the warehouse is 30, right? Number of good item is 4, or defective item is 4, and you have to take out 6 items. You ask the probability that exactly 2 is belong to the defective item, right? P of 2. Okay, then it's just hyper geometric. Same, you put X here, and the number of sample is this guy, right? And population number of population. Yes. Do I answer wrong? AN, okay, sorry. So you just input that up in the reverse order, right? You put the X, small n, big A, and big N. Okay. So I hope you can check it out. This is slightly little bit more complicated for the hypergeometric. Okay. So we can do f of 2 as well. Will be hypergeometric again. Go back here, 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 and here. And then you do true. Okay. So okay. Is that clear? So it does mean that if you in this scenario, 98% of time you get less than 2. What does that mean? In this application, it does mean if you get 3 or 4, okay, it's very rare, right? Right? Only 2%, right? And if so rare that this happened to your audit, then you would not supporting your client's claim, right? Although we don't go to that, but this is the implication, right? Because this said, if this is the case happen, you only get 2 defective items, that's fine. 98. If you get 3 or 4, right, the probability of that happen will be very minimal, right? And then you say, okay, I'm not supporting the client because it will be too risky for me, right? Is that clear? Of course, we don't ask you to do this, but that is how actually being done. Okay, how things being done, but it's, I mean, you learn this in your audit class, so but not our concern. Okay. So after that, we want to tell exponential. Exponential again is the formula is not complicated. Okay, if you recall from that, the big F is 1 minus e lambda x. Okay, and you can see the reason why I do the lambda is because of the case given. Okay. So I think have to be a little bit more careful. I think the Excel you don't put in a lambda, you put in 1 over lambda. Okay, so that's why I put in there. That's why I had a slide called beta to actually do the beta. But anyway, you should put 1 over lambda here. So that exponential. So exponential with a lambda there. Okay. Lambda is 20, but I have 1 over lambda. There's something we care. Is 1 over 20. Okay. And we're going to calculate P of 2, is it? P of 10. We don't have P of 10, right? Because it's continuous. So F of 2. Okay. And for continuous, we don't care about a small f, right? The only calculation is big F. So I just do the exponential distribution. Oh, I forget have x is 2, right? X is 2. I have f of 2 here. So it will be exponential distribution x and in lambda and then true. Okay. Oh, sorry, it's 10. Yes. Okay. So this is the formula. So I have to be careful when you impose the exponential, you not input the lambda, you input the 1 over lambda. So that is slightly little bit trickier. Okay. So that's why when you have to apply to check carefully what is actually input there. Okay. That's why the beta in the slide, because I guess the reason why the beta in the slide. Okay. And now I want to talk about the normal. I guess that's the last one to talk about today. Okay, normal and standard normal. Okay. The normal is rather simple. It's simply normal dist, okay, and mu and sigma and true. Okay. And that is simple. Okay. So normal is like the following. Normal, you have the thing is mu, sigma, x, right? And mu is 20. The question 16 and 16, right? That is the question. Oh, sorry. Sigma is 4. Okay. And we have 1 SD below. The question is what is F16? Okay. And of course, you can convert it to the Z and do the calculation, right? Or f of x, right? That will be even better. So that will be normal dist. Okay. Put the x. Okay. Put the mean. Put the SD, and put true. So this is the F table directly. So you can see it's way much easier. Okay. I can basically simply look at the mu and sigma, then I'm done. Okay. And want to show you how they're related to the standardized one, right? The standardized one is the following, right? The standardized one is actually, this is 0, sigma is 1, right? And this become -1, right? Because this minus this over this, right? I mean, if you want the formula with this, right? We just this minus this and over this, right? -1. Maybe I put it, okay? Maybe I put it here because I guess it's like, I don't know where to put. I don't know where to put. Yeah, it's okay. I do the norm this, right? Put X, put the mean, put SD, and put the true. Okay. So you can see the maybe I can put below. Okay. And the same answer. Right? The same answer here. Okay. Regardless of you look at this and you convert to Z, it's the same. Okay. So that's why I want to talk about the last one, the standardized normal. Okay. Last one, sorry, very quickly, last one is this is norm this is normal table. The stat table is just like norm as this. Okay. So this is the formula that we need today, the last one. So it's a standard normal. It's very simple. We just say Z is -1 and I form P of Z. Okay. It just norm as this of this guy and true. Okay. That's very simple. So this is what we want to say. Okay. So that's all for today. I don't have anything more to say. This is the set table for this one. Okay. So we'll see you next week, and then we'll start to the next topic. Of course, we'll review something next week, but you are able to do all the homework that I assigned. Okay. You can try to check it out. See you next week. Enjoy. No class on Wednesday. Just to remind, I send an announcement again. No classes because of I reschedule it to do the B.A lab later at the end. Do the afternoon. You and your friend guys want me to cover out. It become optional. It's optional class, so it's not more class. Okay. It's